Okay, thank you for the invitation, and I'm very glad to be here to talk about our status of calculation of hadronic tensor on the lattice. So let me first briefly review the hadronic tensor. We know that the double differential total cross section of the inelastic scattering cross sections can be to the leading order observation related to the hadronic tensor and the hadronic tensor. The hadronic tensor, which is the non-perturbative part of the hadron, is actually this matrix element of proton with two vector currents here. For the unpolarized case, the hadronic tensor can be further decomposed into the structure functions F1, F2. And if you want to extract the pattern distribution functions, you can use things like this factorization. Now in the lattice community, many efforts have been done to calculate pattern distribution functions. In our case, we want, on the other hand, to calculate the structure functions directly, which because the structure functions of the hadronic tensor, they have some advantages. For example, the hadronic tensor is scale independent, so there is no renormalization, and the structure functions are frame independent, so we don't need very large external momentum. So if we can really calculate the hadronic tensor on the lattice, we will have how to say, more theoretically clean method to know more about the nuclear structure. To do so, we need to calculate this four-point function on the lattice, which is two currents inserted between the nuclear interpolating field, and this is the normal two-point function of nuclear. And we define this, we call it Euclidean hadronic tensor with the ratio of the four-point function and the two-point function. After we insert some intermediate states, we can show that this Euclidean hadronic tensor is actually a function of this tau, which is the time difference between the two currents. Yes.
It's a good thing.
Yeah, it's good. So the main point is, so we need to calculate this four-point function, which is, I think, the first time that people are trying to do. To calculate this four-point function, of course, there are kinds of ways to do the contractions. On one hand, you can see that we need to add up all the contractions to get this final matrix element, but on the other hand, different kinds of contractions, they are actually different degrees of freedom, which can tell us more about the physics. For example, for this one, first contraction is just the two currents on one part line, which we call it the valence and the Harlan district contribution. And for this, the second one, which is the two currents are on a quarter line that is going backward. So which is, we call this connected state anti-clock contribution. This is according to Kafei's old paper. So this is the reason why we have the Godfrey some violation. This one can explain the difference of the U-bar D-bar contribution. For this talk, I will just focus on the first diagram because this has the best signal. But actually, if this method works, we can have more information from this method. Okay, so now I talk about the Euclidean hadronic tensor on the lattice. after we have the Euclidean hadronic tensor, we need to convert it back to the Minkowski space. As I talked in the previous slide, the Euclidean hadronic tensor is the function of the time difference tau, while the Minkowski hadronic tensor is the function of the angular transfer mu. So to relate it, save.
Save.
What's this?
Save.
Okay, save. Okay. It's okay. Yeah, yeah. It's it's easy to say that connected with this integral form, which is actually the Laplace transform. So formally, to get the Minkowski hadronic tensor, we just need to do the inverse Laplace transform like this. But numerically, we know that we cannot do this integral for our correlators, so we need to solve the so-called inverse problem of the original Laplace transform. But in our case, this tau is some Euclidean times. We have just several other 10 discrete data points for this correlator. But for this this Minkowski hadronic tensor, which is somehow a spectral function, this continuum mu, which has infinite numbers of mu. So we want to review this thing from several discrete data points, which is in principle impossible because we lack enough information. So we call it a ill-defined problem. But in some sense, we can find the most probable thing, image of this thing. So by, for example, some Bayesian method. So I will talk more about this. So yeah, since this is of the central importance of our approach, a general form of the inverse problem is like this. We have some discrete point of this thing tau, and we want a function of a continuum function of mu, and then this is the kernel. The kernel can be different, but in our case, it's just the exponential kernel, Laplace kernel. Although this omega nu is a continuum function, but numerically, if we want to calculate it, we need to discretize it. So, so here I rewrite this integral to some summations. The thing is, how we discretize this omega function is important. If we just want to a rough picture of this omega, we can just discretize mu to some very small number of points. For example, if the number of mu is just less than the number of tau we have, so this is just a question doing like standard chi-square weighting, because the information we have is more than the result we want. If the number of this mu we describe as is equal to the number what we have of this tau, then we need to solve the linear equations. This is just one solution of these equations. However, in our case, to really know about the structure function or this omega function, we need many more points. In numerically, it's usually order of 1,000. So in this case, the number of mu is much larger than the number of tau we have. So in principle, there's no unique solution. We need to plug in some cases or primary definitions or use some other method. So I will talk about some methods we explore. Okay, the first method we can use is called Becker-Gilbert method. This method is just because of the fact that if we have many these kernel functions, then the kernel functions can span a complete spaces of a complete function basis. Then we can find a set of coefficients which can make this, which can combine the kernels to be something like that function. Then, if this is true, we can combine this the coordinates with the same coefficients. Then we can get the function at a particular value of mu there. However, in practice, the kernel functions are far away from building a complete function basis, so which will lead to very bad resolution of this method. The second method we explored is the maximum entropy method, and I call it ME. This method is just a basic method. So the probability, this is a conditioned probability, which is given the data D, a default model M, and some hyperparameter R, which we find the solution function omega, the probability of this is proportional to this e to the q power. Q is this function. L is just it is called the Liang function, which is up to some factor is just the cat square, the standard cat square. S is family thing which is called the Shannon entropy, which is how to say, which is which parameterize the effects of the default model. So if without this S term, the entropy term, so we only have the cat square term, it's just back to our first slide. This has no exclusion. So, but if we plug in this S term, it can be proved that we can find the unique maximum probability of safety. Of course, here comes yes.
So, do you have any physical explanation of why this S function was chosen this way?
This is not. There is no. I think no physics explanation. This is just from some information theory.
Mm-hmm.
So it's called the Shannon.
There must be some meaning to this function. Why?
The meaning is if we know some prior information of the solution of omega, which is this M, then from the information theory, it can come in this form. Yeah, I don't know very much about these details. On the numerical side, this method has these two, I think we can call it disadvantages. One is, okay, sure. One is this. So actually, the parameter of this problem is the omega nu is different nu. As I said, the number of nu is order of several thousand. But numerically, for this ME method, people use SVD. So after you use SVD, so the maximum search is just in a reduced space, which is order of 10, which is makes this possible. And another thing is this hyperparameter R. This is the weight of the default model and the data. So this can be, if this is zeros, then we just have the data. But if this is very big, then what we get is just the default model. So how to handle this alpha is it's not clear, at least for here. People, yeah, sure.
So don't you have the margin against alpha?
Yes. So for this, people use several assumptions like. They have a function of alpha, which is the probability of alpha, and they will choose several value of alpha, which is around its maximum probability, and then do some average about this.
So one thing that I'm confused is typically, so the way that I see this equation is essentially alpha times S, basically a prior multiplying the whole likelihood.
Yes, somehow prior.
E to the minus L is your likelihood function.
Yes.
And then the rest will be some prior. And then
yes.
you You use some form of the prior to avoid, let's say, repeating, or that your session will start basically following statistical observation. The question is, do you need that for the program?
You mean the alpha? You mean alpha S term?
Using the whole, like, I mean, why can I use the analysis just starting with,
M.
you know, yeah,
the number of points you want is much larger than the data points you have.
So I think there are several reasons for the, how to say, theoretical reason is people can prove that if you use only the L term, there is no unique solution of this omega. Only after you have some prior information, then you can have a unique solution of this omega. But numerically, you can say that if you have this L, because you see, for L, you only have, for example, 10 points. But for the parameter mu, you have several thousand one. You can be sure that you can find a meaning, that the L can be very, very small. So that means your chi-square per degree freedom can be somehow 0.1, 0.01. That is somehow overfitting, because if that is true, when you see the result of your fitting, you will see very strong fluctuations. Yeah. So after you plug in this alpha S term, it will somehow numerically heal this. But you're right. So how we choose alpha, how we choose the default model M, this is a big issue. So what we can hope is for the region that our data has very good signal, then the constraint from our data is much stronger than this alpha S term. Then that region is reasonable or reliable. Then if there's a region of mu which depends on alpha or this M heavily, then that region is just unreliable.
Yeah, but you need to produce error band of what is the systematic error of your fit.
You mean systematic error or statistical error? Systematic error, actually, we don't have a very systematic way to estimate the systematic error, but we can vary the value.
I mean, left-hand side of that equation is the probability density of omega.
Yes.
So in principle, if you sample that distribution, you should give the uncertainty associated with that likelihood. Yeah,
but for that uncertainty, I think it's somehow like you can say it's statistical, because for systematic uncertainty, we need also, for example, vary M, because different M can lead to very different results.
So you cannot sample P just because the number of mu's are too large.
I'm sorry. So
you cannot sample P because the number of mu's are too large.
No, we can sample P, but I mean for each M, we can have a P. Is that?
I'm confused. I thought that P is the product density of your omega, right?
Yes. But we are.
M of mu is a parameter function. M of mu is also unknown. Alpha is also in principle unknown. There are many unknowns.
So where is M of mu?
This M is
input.
It's called the default model. It's a Bayesian default model. It's just something you think you know prior to the data.
That's symptotically when you think when it looks like that, symptotically looks up. So that can be a systematic.
Yeah. So I mean, in principle, so the data, the information from the data is not enough to rebuild everything you want. So
right,
we need
but once so for me in basic statistics, once you set the priors, so
yes.
you said what is the model
yes.
of your asymptotic, so that is fixed.
Mm-hmm.
That's essentially your assumption. Given that assumption, given the data,
yes.
then you have a unique probability density for your omega.
Yes.
You just basically sample that probability distribution to get the error. That is given a choice of your priors.
Yes.
Right?
Yes.
Yeah, so you get infinite priors.
Right, but that's the same thing in any field, right?
True. Yes, yes, yes.
Everywhere we will have the same issue, but given the choice, you have a unique uncertainty. So what I'm confused is that you can implicitly, of course, as I was talking about, you need to prove an uncertainty. That means you're sampling that problem density.
Yeah. So because it just asked about, I mean, systematic errors.
Yeah, but,
I don't think that is
in mind, I
systematic
had
error.
exactly what.
But it's okay. Yeah, I know your point. Yeah.
Because that's really what is the error you are making. So you choose a particular minimum, but then what are the variations of that minimum? It's really you're fitting systematic.
Yes.
What Nobu is describing is the way to get an idea of what is the systematic. What are the regions where the data control your output, and what are the regions where the data do not control the output? If you do this sampling, like Nobu is talking about, you will see places where you have a huge variation and places that you don't have a huge variation.
So usually for given the default model M, so the error you get from, I mean, from this probability is much smaller than you vary this M. So this is
how do you compute that error? Do you sample the probability, or you do a Gaussian approximation around the minimum that you found?
Yes, there are some assumptions like for this probability. So, for example, it's Gaussian like around the maximum value. Then,
So, can you repeat again what you said? That the error coming from M is
the error coming from varying M is larger than the error from this.
For a fixed value of,
the probability.
For a fixed value of M, but then that means that the data, the likelihood is not actually providing any useful.
So it's larger, but not bad enough to say there's nothing from the data.
Flat distribution, and I feel like and I get flat distribution, that means that my data is useless. That's how I interpret things.
Yeah, I mean, larger is not that large. I mean.
But there has to be like a some region where the data is constraining.
Yes, sure. So let me continue, and I will show some results then. Yeah. So the last method is called Bayesian reconstruction, which is a new method, and we are working together with Roscoff, and I think this is a very good method. So the point for this method is this is the same function of the probability, and this is just a new Q prime is like this. So there are two differences. One is this term. This is gamma L minus this n tau term. This gamma is numerically a very large number, so which ensures that the L will somehow equals to the n tau, which is the number of the points we have. So which means the chi-square per degree frame is around 1. And they also made a different S. So for this, I don't have much to say why they are using this. If you are interested, you can refer to this function, this paper. So, but there are several numerical advantages of this method. One is they just integral over the Haber parameter R like this. So we got a probability, like I said, of this R, and we integral this alpha over the whole space. And the second one is for the maximum search. In this method, the search is in the entire parameter space, which is ordered several hundred. The search is slow, but it works and it's good. And to make this search possible, and for other reasons, we need high precision architecture for this method. For example, we need to use this 512-bit double number. Yes.
Is the citation correct? It was 1994, this paper?
Oh,
not that early.
Sure. This is no. I'm sorry, it's wrong. It's just I think it's 2014. Yeah, it's a very new paper. I was
2 years earlier.
Okay,
I think yeah. Before this should be correct. But
yeah,
after that.
I do know Alexander, and he looks younger than me. But,
Oh yeah, I'm sorry. That is
So
mistake.
it's only-
I'm sorry. That's a mistake. Yeah, I must copy this somewhere from. Yeah. I'm sorry. Yeah. So okay, so this is comparison the three method. For now, all the errors in this plot is just the error, like you said, is from the probability. There's no error coming from the varying the default model. This is so this is a test for the three method Euclidean two-point functions. The test is based on overlap fermion and dominant configurations, which is at the physical point. This is the last spacing. This test is actually of great importance because we are working on the Euclidean Roper math for several years, and so we tried the variation method and other methods were not actually good, but we found that for we also can use this method, this inverse method, try to rebuild the structure function of the nuclei. The first one is, I need to say, yeah, we are expecting peaks around 1 GeV and 1.5 GeV, which is the nuclei and the the blue one is the result from the Max-Gilbert method. We can see that it's we can see a rather broad peak around, hard to say, 1.5 GeV or something. We can not see any structures here or detailed structure here, but for example, for the maximum entropy of the basin reconstruction, we can see very sharp peaks around 1 and 1. This is actually 1.6. There might be some time space. Please note that the Y scale is the log scale. So actually, the peak is extremely sharp. And one thing we need to say is for the ME and BR. So we can say the BR is sharper than the ME result, and for the ME result, so up to 3 or 5 GeV, there are some fluctuations. I think it's just some unphysical structure, or just because of the method. I didn't vary the default model for this calculation. It's just a test but I believe that if I vary the default model, this peak and this thing can be very different. But for the physical region, it can be much more stable. I have more results of this later.
So what was the default model in this case?
For default model, it's just a constant. The constant is 10 minus 6. 10 to minus 6 power. And so, for example, for this one, for the BR, we can say the value is just approaching the default model for large enough new. There's no information from data. It's just the default model here. So from this test, we know that the BR method is for now the best method on the market. So I think it's rather impressive.
So the other, so you use the constant. So I wanted to ask the question whether you can put some kind of default model in the Backus-Gilbert approach.
And there's no default model. I don't know how to do that.
I do.
I have some questions. I'm trying to understand this. So is the effect of the 3 different curves is just different choices for the fibers?
No.
Is that a simple?
No, it's just different methods. You mean, yeah, it's Backus-Gilbert, the natural entropy, and the basin reconstruction. The default model for maximum entropy and the basin reconstruction are the same. It's just a constant of value 10 to minus 6.
But isn't that the case that we can always cast everything in consultation? Or that's not true. So because if that's not the case, then those three, the bands and the central values of the three things are basically alphas and oranges, right?
Yeah, you mean oranges?
I mean, I would say that the methodology, the physics results should be independent of the methodology.
Yes.
I think that has to be like final goal, right? No matter what you do, you get the same answer, same center value, same answer.
Yes.
But then if the different methods cannot be cast out in terms of probability density, then I have time to try to compare them, right? If they are different,
But I think for this test is fine, because you say for the Bax-Gilbert, so this is what I mean. So for if we only have the error from the distribution of the probability, the error can be tiny. For example, this here the error is tiny, here the error is a bit large, but it's not very large. So, but we can say this is just you say for the Bax-Gilbert method, we just see a very, broad peak here. It means so there are some structures here, but it cannot resolve it. So this is, so this just means you cannot, compare, like data points, or within error bar, they should be consistent or something. It's just this is a bad, reconstruction. If you want to check, one way is to check is for example, up to 3, you can do an integral over this function. The integral value should be somehow similar, consistent, because it's just the integral value will be the correlator you have. So, and for the ME and the VR method, we can say at least up to, for example, 2 point something GeV, they are consistent. And upper and higher than that, so here I just don't plot or didn't plot the error from I vary the default model. But if I add that part, I vary the default model. So we can say the error bar of this part can be very huge, and they will be consistent. I will show some similar plot later. Okay, so I think I need to be quick. So okay, now I talked about how to calculate the Euclidean hadronic tensor on the lattice and how to convert it back to the Minkowski space. So now I need to sketch something about the structure function, so how we would expect it will look like. So I think I would say is just there are 2 parameters. So one is the 3 momentum transfer. This is fixed in our lattice setup of the momentum transfer, and there are also the transfer mu. This just comes from the when we solving the inverse problem. And this thing is this is the gamma proton total cross section plot I got from PDG. This is a similar thing because we can see that at small total energy, there are some structures like this, the elastic one or semi-elastic one, and after, for example, 5 PV or something, there are no structures you can see because for higher energy excited states, they are just a continuum spectrum. So which similarly, we can plot this thing for the structure function. We can expect some elastic peak at small nu, and then semi or elastic peaks or contributions from larger nu, and several GeV above this thing, we can hopefully enter the DIS region, and we call it working region if we want to calculate something related to pattern distribution functions. So for this green part, when you need the energy transfer to be several GeV larger than the elastic peak, and we need U to be smaller than the 3D transfer Q, so we can have physical X and Q squared. One thing is that we later realized that this part, the quasi-elastic part, is also of great importance, because so nowadays the people at Fermi are planning some experimental program of neutrino-nuclear scattering, which they need very precise the neutrino nuclear cross section. The neutrino energy is less than del GeV, which is just this region. Okay, be quick. So after we know all about that, I can do a very simple test of our method. So for example, we can calculate some elastic contribution. So just we use just some vector current, this gamma 4 vector current, and without moment transfer. So if the tau is large enough, this will be just the product of two matrix elements of this one. It will be just the F1 from vector, which is the vector charge. Since we are using normalized vector current, so the vector charge square should be 1. So this is the numerical results. So up to, for example, 6, because this is very precise, up to tau 6, 7, it's very flat, it's 1. So the tail is just affected by the thin excessive state. And so we now have the Euclidean hadronic tensor as function of tau. We can do the inverse. We can use the inverse method to do the inversion, and which is turned out to be so numerical. So theoretically, this elastic hadronic tensor is like this. In our particular case, with moment transfer, suggests that function at 0. So numerically, we can say this is a Bax-Gilbert, this is a matter of entropy. Yeah, they are that function around 0, but this one is much sharper. And another check is because this is the back function, so the integral of this thing should be 1. So we can do the integral over this under this curve. So this one is very precisely 1. This is that's very much an error. So from this test, we know two things. One is that so numerically the Euclidean hadronic tensor is like what we expect, and so numerically, at least for the ME method, it's good. So this is just some setups. I mean, next stage we will calculate the hadronic tensor with this moment transfer. So we need some new lattice, for example, this a nice choppy lattice with very small temporal net spacing, which will help our to reconstruct the image of the spectral function. For other things, yeah, we choose mu to be 1 and P1, Q1 to be 0. So only the F1 spectral function will survive. And whatever it is. So in our calculation, so we choose in lattice unit PQ to be 0.33 and 0-6. So the energy of the proton is 2.15, and we choose a range of the moment transfer to be in 2 to 4 GeV square, and the corresponding X range we can reach is this one is small, but yeah, this is our first calculation. Oh, I need to say more about this because, as I said before, so the Euclidean hadronic tensor is also some exponential behavior. So this En is the energy of the nth intermediate state, and Vp is the external proton energy. Since this is the momentum setup of our calculation, we find that the P plus Q is minus P, which means the lowest energy of the intermediate state, which is this, is equal to the external energy of the proton. This setup, we can say for small tau, so the higher intermediate states will contribute. So this thing will decay.
I'm not catching the dimensions
I'm sorry.
Of that format. The E0, is it like a square? What's it?
You mean E0?
Yeah, why is
Yeah,
it?
so En is
zero square.
Zero square, probably, right?
Oh yeah. Oh
Yeah.
sorry. Yeah.
Okay.
Oh yeah.
Yeah,
Sorry.
Sorry.
Oh yeah.
Okay.
Yeah. So yeah, this is also square. Yeah. Also square root. Yeah. Yeah. So for small tau, this thing will decay exponentially, but for large tau, so the lowest intermediate state will dominate. So this one will just be a constant. Yeah, so this is the numerical results of our calculation. So we can see this is for down quark, this is for up quark. So we can say that for down quark or up quark, they are the same. So for small tau, we do the curve decays exponentially. For larger tau, it's somehow flat. So this one is hard to see because it goes up. The tail goes up, but I think because the thing of the nucleon is just at 20, so this is very close to the thing. There might be, I mean, very heavy excess state contribution, but whatever. So this thing looks like what we want. So then we need to do the inverse transform. So this is the result. So this is for down quark, this is for deep quark, this is for not-limiting method. So we can see that we are expecting the elastic contribution is at around 0 because, as I said, the energy of the low state is the same as the external bottom, but we cannot see any structure around 0, which is because the moment transfer here is very large, so then the form factors here is quite heavy. And after this, around 1 point something or 2 dV, we can see just one structure. This structure is, and I don't think it is a single peak, but this should be some contribution from the quasi-elastic thing. But we can see that this one, although this error is large, but we can see it's somehow stable here, even considering this error. But after, for example, 2.5 GeV, which in the so-called working range of our DS, so it's in this range, it's between these two lines, the error is very large. So this large error is not from, like you said, the distribution for probability. This large error is from I vary the default model. So if the default model, for example, is 0.4, this one is like this. If the default model is 0.01, so maybe get this. So if I vary the default model, I get different number of the tail. But even if I vary the default model, this part is somehow stable. So yeah. So the last thing I want to say is so the lab error of this is just because of the different default model, which means the data has no enough constraint of this region. So why? So okay, this is the result from DR because we are just recently working on this. I don't have a nice thought of how the default model will affect, but compare the left two. This is the wrong label. This is deep quark. I'm sorry. So down quark. The difference is just that they use different default model. This you use the 2 or 3. I remember this is somehow 10. So,
these are quarks in the quasi-elastic peak, or am I?
Sorry.
So can you show that? Maybe I missed the.
I'm sorry.
This is the whole excitation spectrum.
Yes, this is the
whole excitation spectrum.
Yeah, this is the energy of
the whole excitation spectrum. You describe in terms of quarks.
In terms of nuclear.
So why you have the quark contribution?
I'm sorry. Oh, you calculate unity separately.
Yes, the current is for U quark.
Oh, yes, yes, yes. So that's like the quark contribution to the top.
Yes.
Yes.
You can separate.
Yes. Okay.
Yeah. So we can say the position of the peak is similar to what we have for the from the ME method.
Yes.
But the tail is still, I mean, just related to the value of the tail related to the default model. So which still means that even though we use the BR method, there are still not enough information for high energy tensor. So we can have a close look of this issue by looking at the effective mass of this thing. So this is sorry, just yeah, maybe 5 more minutes. So as I said, the EP is around 2 GeV. So this is the effective mass plot of this thing. So we can see at the very small tau, the effective mass is just around 1 GeV, most 1.2 GeV. So since this EP is 2.15, so this 1.25 plus 2.15 is just 3.4 GeV. So this is basically from this plot the highest energy we can have. So how about 2-point functions? So because this is the 4-point function from 2 vector currents, so we can check the 2-point function of a rho method, which is just like 2 vector method. A vector method is just point source. You can say for the effective mass of rho, the maximum value we can reach is around 5 GeV. So this 3.4 GeV is not that 5 GeV, but we think they should be very closely related, because what we can have for this 2-point function can, I mean, give us information what we can have for this 3-point function, because the reason we can not reach very high excitations is because, for example, light spacing or volume or time mass something. So to know about this, we do some very careful calculation. This is something, for example, overlap on domain wall, clover on Hisk, different size, spatial size, different spacing, different time mass. So from this plot, we can say that as a result, this is the effective mass of the rho method. So can be basically grouped into 4 groups. The lowest one is this 2, which is the overlap on domain wall with 0.1 Fermi one. And then this 2 is the clover on clover with the similar 0.1 Fermi. But I need to say these 2 they are anisotropic lattices. This is the spatial lattice spacing, but for the temporal lattice spacing is much finer. And then we can have this one. This is the 0.06 Fermi, and finally we have this 0.04 Fermi, which is here. So we can see that the highest energy we can raise for 2-point functions is mainly related to the lattice spacing. For the smallest lattice spacing, we can reach about more than 9 GeV. So yes, other factors like volume or time mass, they can be, I mean, they can have some effects, but at least they are not significant from this study. And it seems that if we can have this 0.04 fine lattice, our results can be much better. So yeah, let me do my summarize. So we tried to calculate the hadronic tensor on the lattice, which should help us to understand more about the structures. We are beginning to have some preliminary results from this approach. We found that the lattice spacing plays a very important role to reach highly excited states. More detailed investigation will be done for also other factors. Although we don't have very reliable results in the DIS region, but we can have reasonable results for elastic or quasi-elastic contributions, which are also very important. And we are planning to work on lattices with smaller lattice spacings to have better results. Yeah, thank you very much.
Other questions?
Yeah.
Yeah.
Are you trying to study at some point like question of quantum duality? Because I think that's kind of
it's a good question that you raised. We just been thinking about recently because our goal was the formulation was done more than 20 years ago.
Yes,
I never had
at
a
that
chance.
time.
Never thought I would do it in my lifetime.
Yeah.
4-point function and so on. But the computer time comes up very quick, and there are good postdocs. Now the quasi-PDI people, soon figure out. So we were concentrating trying to get the EBS region.
Yes.
As I said, we will look at it. The lattice spacing is not right now, but next few years. But now it's been pointed out to me by Andreas, this is a large neutrino nucleus scattering program in Fermilab. And people don't know what the nuclear, you need to know the cross section in order to get the flux and so on. People can get there's several. If you look at this as a function of energy as function for the nucleus, then you have a quasi-elastic for the nucleus. It's a particle hole, which is 10 MeV stations, which nuclear structure people think they can handle it. But then next one is our, besides elastic, then there's a nucleon quasi-elastic, and this is the region. And that people will find troublesome. It's hard to model it. So what people can do is do in a transitional nucleon to Roper, nucleon to delta, nucleon to N star, and all that. But with this method, it works. Already it's working. You get all some. You don't care to distinguish. In this method, it's very hard to distinguish, but you need a whole total. So you need a cross section, a total. Nu to the 5G. All you care is to the 5G and below and integrated over. And this method, hadronic tensor, is probably the only way that it can handle. The quasi and so on. It's all handled deep elastic. Not a function of nu, but this is a function of nu. You can look at elastic and quasi-elastic, and then eventually deep elastic. So that is the thing that we now start to focus on instead of just looking at deep elastic.
Can I ask a different question? So you showed us these pictures of the elastic peak and or the nucleon peak, and then the Roper peak.
You mean this or?
Yes, Roper peak.
So is there any physical information into the width of that peak?
No, I don't think so, because on the lattice, so if you do the scattering, otherwise this width of the peak just means the resolution of your method. Yeah.
I think it reflects on the lattice space. If you keep the lattice space in 0.001 Fermi, you can get it down.
Yeah.
Because the first one must be a delta function, and it's not a delta function.
They're all
numerically.
Think of how we do variation calculation, or you get a stellar function. Right? That's flats. If you do a fitting, ground state, excited states, all these are delta functions. Here is another way, a third way of doing it. You don't get exactly delta function, but you can resolve. You can get some feedback to the stage.
But actually, for this, we are happy that we can have a peak around 1.5 or 1.6.
Is the Roper unstable over there, or is it a delta function?
Sorry?
The Roper in this particular computation, is it unstable, or is it a...
See, on the lattice, all the states are discrete. There's no unstable states. You're talking about continuum interpretation of lattice. The pi nucleon is less than that. Pi nucleon state is less than that. But what we use is the Coulomb wave function to get rid of the p waves, so that you don't see the pi. Yeah, that's how this thing comes out.
Yes.
Sorry for the interruption.
Oh, sure.
Other discussions? Well, if people are interested, we'll have as I said, lattice discussion tomorrow. But if people want to get around, somebody wants to organize it, we can have an afternoon discussion. Otherwise,
that room here is available.
none of them is available. How about this room?
I'm not sure it is.
We cannot guarantee this.
Okay, tomorrow we can. Tomorrow we have a day, according to the schedule.
We'll double check.
Okay, right. I thought I saw that. So tomorrow we can use and have some slides. Okay, but this afternoon, if we want to get together, yes.
There's also an astronomy colloquium at 4 p.m. I think everybody must have gotten it. Very short minutes, but around different stars.
Astronomy colloquia in my day used to be in the E building, so you just cross the yard down to find the crowds.
Okay.
What's the title? Hard question. Something about
Exoplanet.
terrestrial planets of other stars.
Where you move to the